Hello everyone, this is Danny. This is my first time doing a YouTube live stream. Very excited to be here. If you can hear me okay, we can utilize the live chat to communicate. Great. Uh, let's get started. Hopefully there will be more people joining today. So my name is Danny Wu. I'm assistant professor, College of Medicine at University of Cincinnati. Today I'm gonna share some text mining projects in my lab. And this is not my first time sharing my research with the ACM group. Actually, I shared one of the projects last October. So if you were in that meeting, bear with me a little bit. I think it's still valuable to those who were not in the October meeting. But I brought another project to share with you. So this is the agenda today. I'm gonna talk about first my background experience and then my research interest in the lab. So you know myself a little bit more. And then I'm gonna share with you two projects. One is to use text mining for user needs assessment, and then two is the text retrieval conference, TREC for short. And then I leave some time for question and answering at the end. So my background, I did my bachelor's degree in Taiwan, actually in College of Management. And then I graduated from Michigan with a master's and PhD degree in information science. In the master's degree, I did focused on analysis and retrieval. So a lot of knowledge and skills I'm showing you today actually from the master's degree. And then in the PhD study, I focused on health and clinical informatics. And then after that, I joined UC in November 2016, so about 3.5 years from now. I'm an ACM lifetime member, so I'm always happy to share my experience on my projects with the ACM folks like you guys. And then I'm particularly interested in the computer-human interaction and information retrieval special interest group in ACM. So I would say my experience, a lot of them are very practical. So you can see, in addition to the 3 milestones of the education, at the bottom, I have a lot of industry experience in the telecom company, finance, banking, and then also hospital areas. So I really believe that research can inform practice and teaching altogether. So this is how I look at my research. At the bottom, you see data can be structured and unstructured. In the middle is the data analysis part, and then the visualization part on top of it. And really, my researches are all user-driven or problem-driven, and especially working in the clinical informatics area, I oftentimes collaborate with a physician, either here at UC Health or in Children's Hospital. And from an academic hospital perspective, their major mission is in 3 areas. One for patient care, 2 to do clinical research, and then 3 for medical education. And because my methods are agnostic, I basically do things in all three buckets. But I would say most of my time, well, half of my time actually, uh, have been put into the patient care part. And then the other half I'm going to split between clinical research and medical education. So these are the buzzwords of my research using still the same framework. So from a structured data part, structured data are those in my definition can be stored in a relational databases. I do workflow analyses, system integration to make sure that the data can be used, without barrier, and then fit it into clinical workflow, and then also integrate well. So some data doesn't have to be entered twice, for example, in the process. On the other hand, unstructured data are those like clinical notes, scientific literatures. Those are not cannot be utilized without something like Google. So I did a lot of text mining, NLP, especially in the medical informatics area, to apply those technology and to identify patterns in those data. And then bring those two things together, we'll go to the analysis path. So we can do basic stat summary, some tests, or do data mining, or even machine learning. But I'm very interested in delivering the information to the users. So this last mile of the information delivery is through visual analytics. Can we create, for example, interactive visualization to the users so that they can use their knowledge, they can interact with the information, and then they can identify patterns by themselves. So that actually involves a lot of interface design, usability testing, those type of things. So in terms of collaboration, in my lab there are 3 groups of students. Based on this framework, you probably won't surprise that I have a group of design students help me do the interface stuff. I have computer science engineering students do the analysis part, and then I also have medical sciences students who are knowledgeable in the medical part, and then be able to conduct research, at different levels. But today, I'm going to focus on the unstructured data, and then focus on text mining in particular. Before I move further, I welcome you guys to ask questions during I'm presenting my slides. Just leave a message in the live chat, and then I will stop and answer your questions right away. So talk about project 1, using text mining for user needs assessment. This is a project for Alzheimer's patients. So the principal investigator who has this great idea to develop a mobile application to monitor the cognitive level of potential Alzheimer patients, whether it's diagnosed or not. This tool, through the interaction with the caregivers or family members, will be able to collect the data in the daily activities, and then also show the cognitive level, and then see if it's getting better or it's getting worse. So at this point, the first version of the application was developed by experts, meaning clinicians and researchers, but there's no user study, meaning that they talk to the actual users, which they intended to do. However, conducting user studies could be very time and resource consuming. So what I proposed was whether we can infer those user needs or even app features by some kind of online resources. In this case, the online posts from the health forums. So we basically crawled the online posts from an Alzheimer forum, from this eHealth forum website. And then this is the basic setup. we have two goals in here. One is to infer user needs, as I said, from these forum posts for app design. And the second is to, as a side product, see if we can develop or at least benchmark current clustering algorithms, and then see if we can, automate the text analysis process without human annotators to look at the data for us. So let me walk you through the process. On the left-hand side, you see crawl data, right? So basically, write a crawler using Scrappy to get the data from the website. And then we have two students from medical sciences to help to review the threads because it's a question and answering website. So you can see the posts are organized in the question and answer fashion. You have one question followed by multiple answers. So we merge all the text together to form a thread for each question. So these two students independently code all the threads and then come up with a category, a set of categories. Excuse me. We also calculated the iterator reliability and then solve the conflicts. So this is have a high agreement of 85% of the individual coding. So they're pretty consistent about what they think, from moving from one thread to one of the categories. And then I have another design student, which is the second half of the blue part, to look at those categories and then those threads, and then try to generate personas from those data. Personas are simplified, characters of users, and then to represent user needs. And then after that, the designer write the user story for each persona, and then we infer the app features from it. So based on the blue part, which will be able to answer the first question, and then be able to help us justify some of the design of the application, and then also help us identify more features that the app may miss from the online users. On the other hand, the yellow part was for the second goal. So instead of human annotators looking at those codes and they spend time doing the coding, can we do the clustering? And then how good is the clustering results mapped to the human annotations? So basically, we get the same data. We run a hierarchical clustering methods, and then we have a measure to assess how the difference between this machine-labeled cluster and then the human-labeled results. So I'm going to focus on the yellow parts because I think that will be interesting for the ACM group. So a little bit more detail about the steps. Again, we use Python Scrappy to crawl the data. I have a CentOS server on AWS. We crawled about 400 posts, which can be grouped into 129 threads from about 260 users. And then they're organized in the MySQL database. So for the coding, these two students independently code the data into 9 codes and then 3 themes. I listed the major themes for you for your reference. And then we use FlashCappa, which is a generalized form to assess the agreement between two coders. But if there if there are more than 2 coders, or if the categories are more than 2. And then one of the students in computer science engineering developed actually a tool to help assess the kappa. And then the text mining part comes to the clustering, which is one of the yellow boxes at the bottom. So let me give you a little bit of detailed information about how this text clustering works. We have 5 documents. Okay, these are the 5 documents. I made it up. just one sentence. In the real world, we definitely have more sentences in each document. So first of all, we do tokenization. There are multiple, I do this in Python NLTK, so there are multiple ones. But this one is smart enough to split IAM into two different words, not just by space. And then after that, we remove stop words, because oftentimes they're not very meaningful. And then we do stemming, so that words are in different forms are turned into the same token. For example, if you look at document 2, rained is turned into rain. So it will get matched if there's another term, like in document 5, there's one for raining, and then we turn to rain as well. So once we do the 3 steps, we can create a vector space model. So all the 5 documents, we list all the union of the tokens in the stamped version. And then we basically put 1 and 0s and then see which ones they have. And then we have a very similar similarity score, a pairwise similarity, meaning for any 2 pairs, we calculate the similarity between them, and it's basically calculated based on the intersection over the union. So let me give you an example for similarity, document 1 and 2. You can see at the bottom, the value is 0.25, is 1 over 4. And if you look at this matrix, you can see that the 1 being cat, because there's overlap between those 2 documents. And dog, person, and rain are the other 3 terms that have no overlap. So that's why it is 1 over 4 and it's 2.25. So if you calculate all the pairwise the similarity, you got all the numbers as listed below. And then it depends on which algorithm you're working on. We use hierarchical clustering, so basically look at those who have the highest similarity first, and then group them together, and then so on and so forth. So one possibility is to draw this dendrogram based on the similarity, and you can see that based on the calculation, 2 and 4 are very similar, so they group together first, and then back to 1, and then 3 and 5. So the strength of the hierarchical clustering is you have different cutoff points to generate different number of clusters. In this case, we cut it in the red line, which means we have 4 clusters. 1, 3, and 5 in its own cluster, and then 2 and 4 are grouped into 1 cluster. If we need 3 clusters, we just move the red line up, so that 1, 2, and 4 group as 1 cluster. 3 and 5 remain in its own cluster. So this is there are definitely other clustering methods, but we start with the basic one. So that moves the evaluation part. So how can we know the results of the machine labels are good in terms of closer to the human results? So there are 2 basic ways to look at. One is called purity, another is called rand index. So when we look at purity, that basically means for each machine-generated clusters, what's the biggest portion of human annotated clusters? So if you look at the machine-generated A, there's only A in it, so that's why it's 1.0. If you look at a machine-generated label B, there are 2 labels, and then the biggest portion is A or B, so that's why it's 0.5. So based on this calculation, the average of 4 will be 0.875. But the significant flaw of the purity measure is that we can trick the measure, and then we just assign each item in its own cluster, and then you will get a 1.0 for everybody, and then you get 1.0 for purity, but that doesn't make any sense. That doesn't mean the machine performed very well. So we look at the rand index as an improved measure. So brain index basically use this false positive, false negative, true positive, true negative sense to calculate the agreement. So here we define a false positive as when machine says the clusters are different, but they're actually the same. So you can see that is also a pairwise comparison. If you compare 1 and 2, the machine says they're different, but human says they're true. So that's why FP is 1. So if you do so on and so forth, 1, 3, then let's do it again. So 1, 3, it doesn't matter the actual labels, we'll just judge whether it's different or not. So 1 and 3, machine says is different, human also says it's different. It doesn't matter here is A and C or A and D, as long as they're different, then it's true positive. So once we fill out a form, then we can calculate the brain index, 0.7. Random is also not good enough. There's an adjusted form of it, but because of time, I'm not going to go into the detail of that. But you can see the idea here being we can have multiple data set, not just Alzheimer's. We can have actually multiple clusters as clustering methods, and as long as we have the ground truth of each data set, we will be able to benchmark the data set using different measures. So that's the work we're wrapping up right now, and then hopefully we can prove that our methods, which is actually co-developed with the Digital Scholarship Center, is a better clustering method compared to other existing methods. Okay, so let me stop here a little bit and then see if you guys have questions. If you have questions, you can use the live chat. Okay, I did not see anything at this moment, so let me move on. So the next part of the project is, oh, there's a question coming in. Let me address that. The question was, what's the most difficult part of transforming unstructured data such as the forum post into usable data for analysis? I think the most critical part is to make sure the information is kept in your process. Based on the pipeline I described, we do the tokenization, we remove the stop words, and then we do the stemming. Those are standard ways, but that doesn't mean they fit it into the data itself. Because sometimes stop words may mean things, could have meanings, right? And then also in the medical corpus, there are a lot of acronyms, there are a lot of abbreviations. We didn't take care of that actually in this particular project, and those could be folded into the process and then may not show their value in the analysis. So I think that's the challenging part, that you have to also review the text and then see, if your analysis process actually capture the information in a meaningful way. You can certainly do the run through the pipeline, but if you don't be careful about, if we're not careful about the actual content, then you may not get what you want in the analysis results. I'll stop here and see if there are other questions. Okay, so let me move on to project 2. This is for track. So text retrieval conference is a contest, a competition hosted by NIST. It actually has several tracks. So for example, the newsletter track. The corpus is the newsletter, and then they provide different topics. So you build your own search engine and then retrieve the relevant documents for those topics. I'm interested in because of the specialty in the medical field, so I have been participating in the precision medicine track for years. The precision medicine track previously was called this clinical decision support track, so that's why you see the link is called track-CDS. The what's precision medicine? So it's actually an emerging approach to consider all the individual variations, whether it's in genes or in the environment or even their lifestyle, in social determinants of health, if there's another related term to this. So we try to consider everything so that the treatment can be helpful. So in the precision medicine track, we would like to, focus on the literature search, and then given the topics, can we retrieve relevant biomedical literatures to be able to answer those questions or help to address the needs of the information needs represented by each topic. So this is the track, the detailed information. So first of all, they provide topics. Okay, I share with you topics is usually in the XML format. So this is one topics for in XML part. So topic number 1, you have a disease name, you have a gene name, and you have a demographics. And then usually there are 30 to 50 different topics. So you have the topics to begin with, but really you want to form queries based on the topics, the information in the topics. Second, for the corpus, because it's a precision medicine track, we have 2 types of data. One is biomedical literature, PubMed, and then we have title abstract, and then some full text. It's about 32 to 33 million right now. The other data set is clinical trials. We have all the trial descriptions, eligibility, results, so on and so forth. They're published on clinicaltrials.gov. We have about 335,000 at this moment. So the track competition provides the data as well. And then basically what as a team, anyone can participate. You just need to register, and it's free. So we're competing every time 30 to 40 teams probably around the world. And what you need to do is for each topic, you return the most relevant documents, most relevant 1,000 documents for each one. And what track will be doing is to annotate and then provide, do the human review, and then provide the most relevant the list of documents for each topic for you. And then once we get that, then you can benchmark each team's performance depending on, for example, whether in your results you put the relevant documents on in the beginning of the list. So that involves some standard evaluation metrics, information retrieval. So we're talking about NDCG, program, and then the precision at 10. So because of time, I'm also not going to go into this, but maybe I will go through more if I got a chance to share the results of this research next time. For now, if you're interested in, just look at the link I attached below. Okay, so the question is, are topics the search terms to find the documents? Okay, the answer is yes and no. You could, in the very basic form, just concatenate all the terms together and then make it a search term. right? But this really represents information need. You can do different query expansion to turn those disease and genes into a more appropriate form for query. So they can inform queries, but not necessarily be the query itself, if that makes sense. Okay, so let me also give you an overview of project 2. So this is how I look at it, all the pieces. Each year, by the way, Track has been running about 30 years. So they're very familiar with the process. Precision medicine Track is about 5 years. For every year, the topics will be released, the corpus will be released as well, and then in our lab, we just maintain the latest version of PubMed and clinical trials. So we have a crawler every day to get the latest data from the API in our AWS server. So once we get the data, we fit it in. We have 2 different parsers to parse the information and put it into the relational database, which is MySQL in this case. And as I mentioned, the query expansion is a critical part because it turned the information needs in the topics in the actual query to query against the index that's produced by the parser in the bottom part. And then once you have the query, you have the index, then that's the ranking. We usually use the baseline BM25 and then also tri-language models. And then we also have machine learning components to train and then see if to boost some documents if they're more likely to be relevant than others. So once we get the results, the track will provide the relevant document, and then we basically have our results and then matched with the relevant documents, and then run the evaluation pipeline they provided, and then we get our scores. So this is the basic setup of how it works every year. I also put the technical component on the bottom. So it's basically Python based. So we use Python to develop the parser. We have tried Lucene and then now Elasticsearch for the ranking, for the search engine itself. Seems that Elasticsearch is much easier to work with than Lucene, so we're going to stay with that for this year. And the Python component to re-rank and the machine learning component part to re-rank the documents and then generate the results. And lastly, there's a Perl script that provided by Tract for the evaluation pipeline. So I also want to introduce you, even though we don't have time to go through the details of evaluation, but two very basic ideas about information retrieval. So basically, look at the graph on the left. Again, this is from Wikipedia, but let me go through that for you. You have a set of documents, right? And then on the left-hand side, they're relevant. On the right-hand side, they're not. And then given the query, you basically hit some of them, right? So if you hit the darker part, that means it's true positive. The ones you hit are the actual ones. But if you hit the other half, the lighter part, that means they're not relevant, but you say they're relevant. So that's a false positive. So 2 very basic but important ideas of the performance of retrieval results is precision and recall. So precision means for the things you retrieve, how many of them are relevant. Okay, and you can see the sort of graphical representation on the top left. For the bottom is recall. Among all the relevant documents, how many of them you retrieved. So you can see the functions are very similar, but the denominators are different. So let me give you an example. So let's say we have 1,000 documents. Two of them are relevant for this particular query. And your system, or you develop a system, given the same query, you get 100 documents, right? 10 pages, and then 50 of them are actually part of the 200. So based on the calculation, the precision is 550 over 100. So among the 100 you return by the system, 50 of them are relevant. And then you can see we previously used precision at 10, meaning we only look at the top 10. Okay, so this could be rephrased as precision at 100. We look at the first 10 and then see how precise they are. This is because usually people in the search engine will not look results after the third page. So we usually look at precision at 10 or 20 to benchmark the performance. For recall, because there are 200 in total, we only be able to hit 50 of them. So based on the calculation is 0.25. And there's an F score, combining precision and recall. But usually precision and recall are a trade-off. It's a trade-off because sometimes you focus too much on precision, you want to make it accurate, then you miss a bunch of things that should have been included. On the other hand, if you try to be very inclusive, you can be, in the extreme case, you just get everything. And if you get everything, the recall will be 1 anyways. The precision will be pretty low. So it's a trade-off usually between precision and recall in benchmarking the retrieval system performance. So there's a question coming in. How do you decide if a document is relevant? Well, that's a good question. Usually it's determined by human beings, okay, in this type of competition. It's very similar to the coding process we did before. We have a person look at a query, and then we have all the results from all the teams, then merge them together, and then look over the top ones and then determine this is relevant or not. And then they have maybe 2 people work on the same tasks, and they have agreement and see if they agree with each other to a certain percentage to create a ground truth. But in reality, it's not gonna be easy, right? So when you are searching stuff, it's hard to determine the relevance right away, and then to tell Google that this is right or not. So there are other ways to provide relevance feedback. For example, if you click something and then bring it up, then we can fairly assume that this is somehow something relevant. And if we collect enough clicks from the users, then the ranking can be adjusted based on that. I hope that answered the question. So what we did, I have a team called CNC Med IR. We participate many years. I'm going to show you 2 of the years in 2018 and 19. In 2018, we were actually partnering with the Michigan folks. In this task, we use Lucene as the search engine backbone, and then we use BM25 as the language model. And we did a little bit work on the query expansion part. Basically, if you look at the middle, we have 4 different strategies to expand the queries, and then we set a threshold of 500. So if the strategies execute the strategy from 1 to 4, and we stop when the number is filled. So if the first strategy generates enough numbers, then we stop over there. If not, then we execute the second, third, and fourth. Different strategies expand the query differently, and then get different results. If you're interested, I can send you the manuscript for review. We also have a machine learning part, which is a classifier, basically indicate whether this is a relevant or not a case. And then we re-rank the results. We basically move the possible relevant documents on the top, and then move everything else at the bottom. So we learned from that process a little bit, and I figured out that actually a lot of relevant documents are covered in the first strategy. So in 2019, we switched the goal a little bit, and we did not work with the Michigan folks. We tried to be independent on our own. And then we use Elasticsearch because we figured out losing sometimes it's a bit hard to work with. But we still use BM25 and language model. By the way, each year you can submit multiple runs. You can have different combinations of algorithms, different combinations of expansion, and then then you can see which part can contribute to or undermine the performance. So similar to 2018, but we only focus on in the query initiation part, but we only focus on the first strategy. But on the other hand, we have two things to add on. One is the concept-based retrieval to improve the recall. Studies have shown that if you retrieve based on the mathematical concepts, not the actual word, you're more likely to improve your recall, which is reasonable because if you think about a case where you're searching the medical documents for hearing loss, you might want to get documents with difficulty of hearing, right? But those things, they're in different words. If you don't do NLP to recognize their concepts, you will not be able to treat them as the same in the retrieval process. So we basically implement that concept-based retrieval, and then using the tool that NLM, National Library Medicine, provided called MetaMap. And then we implement that concept-based retrieval to improve our recall. And then on the other hand, we suspect that the relevant documents are from top journals. So we basically say, okay, we treat the 2018 relevant documents and their journals as top journals. So whoever in 2019, if you appear in those journals, then we boost it a little bit. And those are two very simple mechanisms. And then compared to other teams, we use sophisticated mechanisms. We were hoping that we can get comparable performance. And we did, so which is very surprising and then interesting. So we didn't do much, but we still maintained a good performance. Probably, among the 30 teams were between top 5 to 7-ish. They only announced top 10 for each major, but we're between top 2 and top 7. Which is encouraging because we want this to be implemented and used in the real world, especially with for the collaboration with the Digital Scholarship Center. So too much training in the other parts may not be feasible based on our resources. So for other teams, they're also using Elasticsearch. They have sophisticated query expansion, which could be helpful and then boost the performance a little bit. But that requires a lot of outside databases and then maybe sophisticated mechanisms to expand the words. And then other teams also use learning to rank and then other AI-based algorithms to rank the documents, which may also improve the performance. But as I said, we'll be able to maintain comparable performance last year. So goal for our team for 2020, well, I'm not sure if it's actually going to be happening given all the coronavirus pandemic, but we still have a plan. We want to utilize all the relevant documents in 2018 and 19. We want to train a machine learning algorithm, but again, we're going to maintain our style. We're going to look at some simple and then elegant features. So we are exploring that. And then, so for example, one thing we call the recency seems that all the relevant documents are more likely, within certain years. So if that's a critical feature, we can throw that into the machine learning model. The other possible feature could be readability. So if the assumption being that if the document, the text is more readable, maybe they're more likely to be marked as relevant. So we're experimenting different features and then hopefully train the machine learning classifier to re-rank the documents. Yeah, so another question coming in asking how much of an impact does machine learning have on the search? Okay, so I think that's a fair question, but I will not know until we have the data, right? So I think this is actually the right time to answer that question because we have 2 years of data. So if we can develop a pipeline and then have the baseline value, and then we can say, control everything else the same, adding this machine learning, how much, performance gain do we get? And then that's the value of the machine learning algorithm. And then if the performance gain is not much, then actually it's not worth the time to do it, in my opinion. Or we can explore different algorithms and then, benchmark and then see, how much they will improve the performance. So I think that's all I want to share for the track project. I would like to utilize this opportunity to recruit students very interested in working with ACM group, and then actually Piyash Sahu is one of my students now. I think the best way, as I described before, I have 3 groups of students. The design, usually coming from the Master of Design program and psychology. The research team, mostly from medical sciences. The technical team is from computer science engineering. So the best way to work with me, I think, is through this, based on the different models in the past years. I think this is the best, is to do a research EEP internship position. If you don't know what it is, it's a unpaid co-op substitute. Everyone can do one. It will still use CPT, by the way, if you're an international student. It's usually 4 days a week for 15 weeks to fulfill the hours, but you will learn significantly for Linux server management, algorithm development, like the work we do, and then work with an interdisciplinary team. If you're interested in the job ID in the PAIL system is listed over here. I think this is more suitable for people who are doing their first co-op or the last co-op. If you're interested in research, and then unfortunately I cannot pay you because that's how the research EEP intern is defined. It has to be unpaid experience. But I guarantee you that you will learn a lot, and then especially the opportunities to go to a conference, publish papers, and then also work as a part-time when you are in the not in co-op in the later years in my lab. Okay, I think that's all I want to share. Again, very happy to be here and then share my research with the ACM student group. And I'm happy to do it again when time permits, and if you guys are interested. At least my contact information here. If you have questions, feel free to leave a message in the live chat or send me an email afterwards. I'll stay here a little bit longer to answer the questions. Thank you. Okay, it seems that there is no question. I'm gonna end the live streaming. So good luck to your studies and your finals, and then stay safe. Bye, guys.